I want to say a very big thank you to the REFPROP team at the National Institute of Standards and Technology for giving me permission to use their mini REFPROP program. So all the charts you see me plot are plotted using this program. And the incredible thing is it's free to download. Check out the description for a link to get the download. I think it's incredible that you can just have access to all of this. So thanks again. Here you have the pressure enthalpy diagram for water. Here it is for air, for carbon dioxide, for methane, for hydrogen, and for the refrigerant that's sitting inside your air conditioner or your fridge right now. It's called tetrafluoroethane, or given the number R134A for short. Now these are very different chemicals. In fact, air is not a single compound, but a mixture of them. Some are essential for life, some will kill you. The presence of some of these in our atmosphere drive climate change, while one of them is being sold as the solution to it. Some are explosive, some are gases at room temperatures, while one of them is a liquid. In fact, one of them will go directly from being a solid to a gas at atmospheric pressure without ever going through a liquid phase. Despite the fact that we know that these are very different chemicals and they behave totally differently, we can see that their pressure enthalpy diagrams don't look that different from one another. And that's why I think that if you can navigate one of these, you are well on your way to understanding basic chemical thermodynamics that you need to use in situations that come up in process engineering. To start, let's look at the pressure enthalpy diagram of water. The first reasonable question to ask is, what is enthalpy on the x-axis? The thermodynamic answer is enthalpy is a thermodynamic quantity that equals the sum of the internal energy as well as the pressure multiplied by the volume of a substance. So that's a way of answering the question completely correctly and not really explaining anything at all. And this is why thermodynamics has quite a reputation for being unintelligible and is perceived as a difficult subject. A lot of thermodynamic quantities are not things that we can simply measure by sticking a probe into it or using a ruler. Quantities like temperature, pressure, and volume are all intuitive because we have the tools necessary to measure them. Enthalpy can only be quantified by measuring changes in those other measurable variables. We don't need to go down a thermodynamic rabbit hole in order to understand it though. Think of it as the energy content of our substance, and the way you increase something's enthalpy most easily is by heating it up. So in order to move from left to right on our x-axis, we heat something up. In order to move from right to left, we cool it down. So I'm using the term heat up and cool down very loosely. What we mean by that is we're saying increase or decrease something's temperature by removing or adding heat. And that is usually done by contacting it with something that is hotter or colder. But anyone who's ever pumped up a bicycle tire knows that after a while the pump itself gets hot. Here we have a vacuum cleaner. A vacuum cleaner is simply an air compressor. It takes air and sucks it out of the business end and spits it out of the back. The movement of that air creates a low pressure at the point at which you are sucking or vacuuming up. That's why it's called a vacuum. A vacuum is simply any pressure below atmospheric pressure and cleans up the mess you've made. Now, I've stuck two thermocouples onto this vacuum cleaner, one at the inlet, one at the outlet. Let's see what happens. Look at what's happening. The outlet of the vacuum cleaner, in other words the bottom reading, is higher than the inlet because the act of compressing that air heats it up. Take a moment to appreciate what that means. It means that I can increase something's temperature without needing to transfer heat to it from a body that already has a higher temperature. So that is why we have this quantity called enthalpy. It is a quantity that allows us to calculate the energy changes in a system due to both direct changes in its temperature due to heat transfer, as well as by virtue of the fact that it may be compressed or expanding. And so that's why I say when you're using these diagrams, it's good enough to think of enthalpy on the x-axis as the energy content of whatever it is that we're studying. On the y-axis, we have pressure. Whenever we're dealing with thermodynamics, we're talking about absolute pressure. Also note that the y-axis is a logarithmic axis, meaning that the pressure jumps from 1 bar to 10 bar to 100 bar for equal step sizes. If it wasn't like this, this chart would be a lot bigger. Now you may ask why pressure, and that's a fair question. It doesn't have to be pressure. Here I'm showing a chart where we've plotted enthalpy against temperature instead. These two charts show identical information. It's just that we've forced curved lines on one to be a straight axis in the other. At the end of the day, it's what you're used to working with, and some charts are better in some applications. Another common type of chart is an enthalpy-entropy diagram, which is commonly referred to as a Mollier chart. The important thing to note is that the information in all these different types of charts is the same. It's just the axes that are changing. The thermodynamic information of steam has to be what's in the steam table, and it can't be a function of the axes you pick. I like working with pressure enthalpy charts because, like I said earlier, I'm comfortable with them and I know how to navigate them. Right, so we've discussed the axes. But now what about the actual lines themselves? The lines we are seeing are lines of constant temperature. Here faintly in blue, I've highlighted the 25 degrees Celsius line. Here highlighted in red is the constant 100 degrees Celsius line. I tend to see it like a tablecloth or a towel or something falling on top of this big bulge in the middle. I get that that doesn't make sense because it's straight across in the middle, but the point is everything to the top right of this line is above that temperature, while everything below the tablecloth is under that temperature. Now there's all sorts of other lines that we can get on these diagrams. I've omitted them here just for clarity, but here you can see what it looks like when I add constant density lines. Now density is kilograms per cubic meter, but sometimes what is plotted is specific volume, which is just the inverse, meters cubed per kilogram. It doesn't change what the lines look like, it just changes the number next to them. Here we have constant entropy lines. Now without going too deep into entropy, know that you don't need a fundamental understanding of it to know that these are the lines that we use when we're looking at gas compressors, as well as gas expanders or turbines when we're doing work or getting work out of a gas. And finally, lines that show me the relative amounts of vapor and liquid. If the substance I'm looking at is water, then I'd call this steam quality. Now, all of this information is the information you'd get if you decided to take your steam table and plot every single value in it. Pressure enthalpy diagrams, temperature enthalpy diagrams, entropy enthalpy diagrams are all various iterations of the same data. So we go back to our pressure enthalpy chart for water, and I'm going to remove all the lines except the constant temperature lines again for clarity. And that's the beauty of this mini REFPROP program, is I can just remove and manipulate the information I show so that I only have what's relevant. So I've said I've removed everything except constant temperature lines, but that's not exactly true. The big question is, what is this shark fin, this big bulge in the middle of the chart? This area is the two-phase region, meaning there are two physical phases that exist. Phase, we're talking about solid, liquid, or gas. Before we look at the two-phase region, it may make sense to look at the single phases. The first thing I want you to do is take a horizontal line and lay it on top of this two-phase region. So it's just going to touch the tip of this region. Because it's a horizontal line on a pressure enthalpy chart, it is a line of constant pressure. Everything to the left of our two-phase region is a liquid. Let's prove that to ourselves. The water coming out of our tap is, let's say, at 25 degrees. Here's my tablecloth from earlier indicating the 25-degree isotherm, in other words, constant temperature line. Here is the horizontal line that indicates a constant pressure of 1 bar. 1 bar is roughly 1 atmosphere, the pressure of the water as it comes out the tap. Remember, we're talking about absolute pressure, not gauge pressure, otherwise the gauge pressure would be 0. And so you can see the intersection of these 2 points clearly shows that we're comfortably in the liquid region, as you would expect for water coming out of your tap, unless you live in some ridiculous place. Now, do you remember what I said about moving from left to right on this diagram? That the way you do that is to heat something up. Well, what happens when you heat up water that comes out of your tap? That's right, we've already got a term for this. It's called boiling a pot of water. Here's a video to entertain you. So what you see in this video, first of all, is that I'm boiling water. The pressure of that water cannot change because the kettle is open. Right, so that water is constantly at atmospheric pressure or around 1 bar. A process that takes place under constant pressure conditions is referred to as isobaric. So me boiling a pot of water is an isobaric process, and I represent that with a horizontal line on a pressure enthalpy chart. So you've just witnessed the water being heated from 25 degrees to 100 degrees. I've highlighted both of those lines on the chart. So the water went from point A at room temperature to point B at 100 degrees along a horizontal line, which is that constant pressure line of 1 bar. That is the isobaric process of heating the water to its boiling point. Now we're watching this water boil. Can you see no matter how long I let it sit here, the water temperature cannot go above 100 degrees. And that's because that is the temperature at which water boils at 1 bar worth of pressure. Here you can see me sticking another thermocouple underneath the kettle. So we're measuring the base of the kettle. And you can see that the kettle itself is actually at a higher temperature. It's at 110 degrees. It does not matter what the temperature was. It could be 300 degrees, and I would not be able to raise the temperature of the water above its boiling point as long as the pressure remains 1 bar. And that is exactly what this chart is showing us. As we get to point B, where that liquid water reaches 100 degrees, adding any more heat, meaning moving left to right to try and increase this water's enthalpy, will not change its temperature. This 100-degree line is horizontal, and I cannot change that temperature of the water once it starts to boil. So the only way of increasing the temperature at which the water boils is by increasing its pressure. And that is exactly what a pressure cooker is. Here you can see I've slipped a thermocouple past the seal of the lid of a pressure cooker, and now we're going to observe what happens. Note that you shouldn't stuff around with pressure cookers too much because, of course, it is dangerous, it is steam, it is under pressure, and you can lose an eye. So where previously, because of the open kettle, we couldn't achieve more than 100 degrees, now that I'm building up pressure inside the pressure cooker, I can go past that 100 degrees and actually build up to 110 degrees in temperature. As soon as I open the vent and I release all of that pressure, my temperature plummets because the water cannot exist at 110 degrees at atmospheric pressure. So the temperature drops from 110 to 100. The temperature I achieved in the pressure cooker was 110 degrees, so I've indicated this constant temperature line in yellow. If we look on the y-axis and read off the pressure, we would find that the pressure to achieve boiling water at 110 degrees is 1.4 bar. That's referred to as the saturation pressure. Okay, I didn't really read it off the chart because the chart isn't very accurate. I got it from a steam table, but you get the point. So this is what people mean when they say water boils at a higher temperature when the pressure is higher. And that's why your cup of tea is warmer if you're at the coast than if you're sitting in the mountains. And that's because atmospheric pressure is higher at the coast and starts to decrease as your elevation increases. A quick Google search tells me that typically you can reach a pressure of 2 bar absolute, so around 1 bar gauge in a pressure cooker, which means you can achieve a temperature of 120 degrees. Now there's something really important you need to understand about the two-phase region. When we started boiling the water, we moved from point A to point B. Point B is what the liquid is experiencing. It lies on what is called the saturated liquid line. Saturated means that any additional energy given to the liquid will cause it to boil. There is no single water molecule that exists inside this two-phase region. All the liquid in the bottom of the pressure cooker or in the bottom of the kettle exists at point B. Once I give a water molecule enough energy to escape the liquid phase, that water molecule immediately jumps over to point C. Point C lies on what is known as the saturated vapor line. Saturated vapor means this vapor is about to condense. You take away energy from it and it will turn to liquid. So that means that everything to the right of my two-phase region is a vapor. So all the liquid that I have in the bottom of my pot, that exists at point B. All the vapor, the steam, the stuff that is boiled off, those molecules lie at point C. So the only thing that really exists in the middle is the mixture as a whole, as opposed to any individual water molecule. So when we started with only liquid, it's saturated, it's about to boil, that was at point B. As more and more liquid turns to vapor, the mixture as a whole moves into this two-phase region. When I hit the middle of the two-phase region, it means that I've boiled off half of my water, meaning 50% of my water is a liquid at point B and 50% of the water is a vapor at point C. If you think back to the beginning of the video when I was showing all the different lines we can show, one of them was the one I referred to as the steam quality. And that's what these lines inside this two-phase region are. How much of my mixture is liquid? How much of my mixture is vapor? The distance between points B and C, if we follow them vertically down and read that change in enthalpy, that distance is the amount of energy needed to boil a kilogram of water. This is called the heat of vaporization. It's the amount of energy we need to put into the liquid water in our kettle to boil the water, and it's the amount of energy we will obtain from the steam when it condenses. In one instance, we're moving left to right. In the other, we're moving right to left. But the amount of energy doesn't change. We can do a similar thing with points A and B. The amount of energy needed to heat up the liquid water from A to B is known as the specific heat of the water. This is given the symbol Cp, and this should start making sense now because Cp is the specific heat at constant pressure, and like I said earlier, all constant pressure lines are horizontal. I should say that the distance between A and B is actually not the specific heat, because specific heat is for 1 degree change, whereas A and B represents a 75-degree change. But you get the idea. The thing to take note of is that the distance between A and B is small, while the distance between B and C is significantly larger. So it doesn't take much energy to heat water from 25 to 100, but it takes a lot of energy to boil that water from B to C, even though the temperature of that water hasn't changed, only the phase has. This is why we love steam. Steam can carry an incredible amount of energy in the form of latent heat, that heat of vaporization. So the distance between my constant temperature lines, that is my specific heat. You can see the lines are a lot closer together for the vapor than they are for the liquid, which means steam has a lower specific heat than liquid water. That means that the same amount of energy will heat up steam more than it would liquid. The other thing is specific heat is not constant. The gap between these lines changes and is a function of pressure. At very high pressures, you can see these lines come really close together, and so it is very easy to heat up steam at very high temperatures and pressures. This is also true for the heat of vaporization. Have a look at how much less energy I need to boil water at 100 bar compared to what I did at 1 bar from points B to C. In fact, if I increase the pressure enough, the length of this line will get so short that eventually it will disappear. And that happens right at the top of the shark fin. That means that at a high enough pressure, it takes no energy to boil water and change it from a liquid to a vapor. So that leads us to ask, well, what's happening at the top of this chart? This is why I asked you to put the horizontal line across the top of the two-phase region when we started. Now, rather than looking at the pressure, let's look at the temperature instead. Do you remember my tablecloth from earlier? Imagine I'm putting that tablecloth down and I stop the moment the tablecloth touches the top of my two-phase region. This is what I get. This temperature is known as the critical temperature of a substance. For water, that temperature is just shy of 374 Celsius. Above this temperature, it isn't possible for me to liquefy the water no matter what I do with the pressure. And you should be able to see that from the diagram. I only have a two-phase region. I only have a region with liquid in it underneath the tablecloth. If the idea of something being above its critical temperature sounds crazy to you, it isn't. We can think of a real-life example where something is above its critical temperature. Let's go back to the pressure enthalpy diagram we had for air. I've highlighted the critical temperature of air, which is roughly minus 140 Celsius. That means that the air in your room, which is sitting at 20 or even 40 Celsius, cannot be liquefied no matter how much pressure you apply to it. Even if you were in Siberia in the middle of winter and the temperature dropped to, say, minus 50, you still wouldn't be able to liquefy the air. So when we perform air distillation to separate oxygen and nitrogen, we have to cool to at least minus 140, but to get any significant amount of liquid, it's got to be a lot colder than that. And that's why air distillation can take place at temperatures around minus 200. Can you see how useful understanding pressure enthalpy charts is? We've spent the last 20 minutes looking at the pressure enthalpy diagram of water. We quickly shift to air, and all of a sudden we start understanding something about air distillation. Let's go back to water. This critical temperature corresponds to a critical pressure, which is that horizontal line I asked you to draw earlier across the top of our two-phase region. The critical pressure is simply the pressure required to liquefy a substance when it's at its critical temperature. For water, that's 221 bar. Why don't we go look at our air example? For air, we found that the critical temperature is minus 140 degrees. The corresponding critical pressure is around 37 bar. But we don't need our distillation column to operate at that pressure because we're going lower in temperature down to minus 200. The column can operate at a few bar. So let's go back to our water. Here we have the critical temperature and pressure. Earlier I showed you a diagram labeled as follows with the different phases, but technically that vapor phase is too big. We need to remove everything that is above the critical temperature. And then everything that is above the critical temperature or above the critical pressure we refer to as a supercritical fluid. A supercritical fluid is anything that exists above its critical point, and the critical point is the tip of our two-phase region. Now the problem with indicating it like this is it shows very hard discrete boundaries between the liquid and the supercritical region and the vapor and the supercritical region, which makes you think that something magical instantly happens, and that's not the case. When you have a supercritical fluid, it means that it becomes very difficult to distinguish between the liquid and the vapor phases. That's why boiling the liquid at the critical point takes no heat of vaporization. The difference between the phases is difficult to distinguish. If you look up phase diagram on Wikipedia, you'll find the following for water. You can see we've been playing in the region between gas and liquid, and that solid line is the two-phase region. It's just shown as a line here, whereas on a pressure enthalpy chart, it's shown as an area. You can see as we start approaching the critical point, they intentionally blur the colors into white into both the liquid and the gas phases, and that's because of this difficulty in making a distinction. And there you have it. Pressure enthalpy charts are my way of getting my head around any problem in thermodynamics. There's just something about plotting points onto this chart that helps me understand, okay, what phase am I dealing with? Which way am I going? We've only touched a few of the things that we're likely to come across. But if I go back to showing you the original pressure and enthalpy charts of all those various different substances, you can see why knowing your way around this is a really good start.